For being here today in person and for being out there in Zoom land. Welcome to the first astrobiology seminar of the quarter. This series was put together by Professor David Catling, who I am not. David unfortunately couldn't be here today, so I'm taking over the honors of introducing our two speakers today, who are both local here to the University of Washington. They're both going to talk for about 30 minutes. So first up is going to be Professor Jim Davenport here from the astronomy department, who's going to be talking to us about stellar cycles, stellar activity, magnetic fields, and how that is relevant to astrobiology. And then second we'll have Caitlin Rasmussen, who will take over at the bottom of the hour. So Jim has been here for a long time, including his undergraduate years. So he is old school, and so it's great to be welcoming him into the astrobiology program. And this is part of the requirements to join our program is to present some of his research to all of you. So I'm just going to turn it over to you and stop wasting time and please take it away.
Great. I thought I was past my exams, and instead I have a required talk, as Rory said. So I hope I pass. So hello, it's nice to see you all and see you all on Zoom land, although I can't actually see you because I have everything hidden. So if you have a question, I can't see it, shout out, please interrupt me. As Roy said, I have been at the University of Washington on and off for most of my career. And so it is really a great joy to get to participate and to talk to the astrobiology group, which has been such a powerhouse throughout most of my time here at UW. And I've been really fortunate, as I've listed here, some of my collaborators who are relevant to the astrobiology program and who many of you know. Particularly, I've been doing a lot of work in the last few years with Rory, with grad students Lupita and Tyler, on projects relating to stars, which I'll talk about today. Former grad students like Brett Morris, who some of you may have known, and also Rodrigo Luger and others who've come out of this illustrious program. So it's been a joy to participate and collaborate over many years, and I'm really looking forward to being able to participate further as a member of AB in the coming years. So I'm going to talk for about 20 minutes about stellar magnetic activity with Kepler and TESS, my two favorite telescopes, my two favorite missions here shown, Kepler on the left, TESS on the right. Now, you may know these as exoplanet hunters, as missions focused around planets, which is probably in more of your wheelhouses in the astrobiology program. But I have unfortunate news, which is they are actually stellar astrophysics missions. And we realized this shortly after launch when we saw data like we see here on the left, which I'll talk more about today, that these are stars missions, not exoplanet missions. They just happen to find some of these pesky exoplanets. And so this has been a great boon and really a great revolution in how we understand stars like our sun, and particularly stars smaller than our sun that inhabit our galaxy. And I'm going to talk about stellar magnetic activity, but at the very end, I'm just going to sort of leave an open-ended invitation to come chat with me about anything related to stars that strikes your interest. Weird stars, small stars, rare stars, even aliens and things that we might not expect to be hiding in our data. Okay, so the underlying theme of my work, especially with regards to missions like Kepler and TESS, is trying to understand stars like our sun, coming from a background of stellar astrophysics. And this obvious statement that the sun is not constant in time. Right? Over short time scales, like we see here, this video from NASA's Solar Dynamics Observatory, this is over a couple hours, the sun is very clearly not constant, right? If you look very carefully when the video loops, there it goes, you can see the sun is very slowly rotating. It rotates about once every 25 days at the equator. There's a small rotation here. And there is this very dramatic flare event, which you see happening in sort of the upper left quadrant of the sun. Over a couple hour time scale, the sun emits a whole bunch of ultraviolet and X-ray radiation. There's obviously material coming off the sun in this coronal mass ejection, this prominence that sort of snaps and flies off. These can be bad news if you're trying to form a baby planet with maybe life around it. So over short time scales, like we see here over a couple hours, the sun is not constant in time. And so when we stare at hundreds of thousands of stars for years on end with missions like Kepler, we expect to see this variance, this variability. And this is exactly why I dropped what I was doing in 2009, 2010, after the Kepler mission launched. And we saw a light curve very much like this one. And it was, in fact, this M dwarf right here, GJ1243, that caused me to drop what I was doing and turn into a stellar activity and a time domain astronomer. And I have sort of maintained that ever since. This star is a very nearby M dwarf. It's about 20% the mass of the sun, so it's a low mass star. It's only about 12 light years away. It's very nearby. And you can see the light curve, the flux over time, is highly non-variable, right? It's not stationary at all. There is this sort of 2 to 3% modulation that we see every 14 hours. The sinusoidal modulation, that's the star rotating. There is a large star spot or a group of star spots on the surface, which cause this really dramatic 3% modulation over time. This allows us to measure the average rotation rate of the star. Again, I said the sun rotates every 25 days. This star rotates every 14 hours. So it's very rapidly rotating, probably because it's young. There also are obviously these lots of little spikes, these little impulsive peaks in the light curve, randomly spread out throughout the light curve with a variety of amplitudes. I've chopped it off here at a few percent. These things go up to 50% amplitude in most cases in a given month of data. This is just a 4-day snapshot of this star. So you can see in this 4-day snapshot, there is something like 50 to 70 of these flare events, these explosive transient events. These things happen once every hour or two. And the moderate sized ones you see here, sort of the middle sized spikes, are about the same energy as we see on the very largest flares in the sun. So this small young star is very active, magnetically active. These are magnetic explosions on the surface of the star. And it's happening very frequently. So this is an environment that a young planet would be experiencing. Again, it's 20% the mass of the sun. So if it was in a habitable zone orbit, it would be very close to its star. It would be right up against these flares that are going off every few hours. This would be probably a very difficult place to have a picnic. So it's this light curve that I found really entrancing and wrote a series of papers on this for my thesis. We ended up collecting something like 11 months of data like this. This is 4 days. We collected something like 300 days worth of data like this over several years from the Kepler mission. And we did a bunch of really amazing things. One thing that I found really interesting, which Lupita has repeated in her thesis work recently and done a much better job at, is taking all the flares that we have observed from this one star and stacking them on top of each other. Some flares are big, some flares are small, some flares have long durations, some flares are very short. But when you stack them and scale them all by their sort of amplitudes and durations, you see that they all sort of follow this general shape. They all are very well behaved. Like the big ones and the small ones all sort of seem to be drawn from the same physical processes, the same emission and decay processes. This is something to do with the temperature and the density of the atmosphere and how fast this plasma can cool when it's heated. Lots of physics going on here. But this empirical flare shape has been extremely useful. We made a version of this back in 2014, which has been widely used in the community to study flares, but also to remove flares as a, I don't know why you would find them a nuisance, but some people do. So removing flares from your light curves, say if you're interested in transiting exoplanets and you have a flare that goes off and you need a model to remove it. So this is now the best model that we have available, and it's analytic, it's fast, it's differentiable, it's really a great model. Lupita's done great work here. This empirical flare shape is really fascinating. This is just one star with one telescope. I'm jumping ahead to my next favorite telescope, which is TESS, slightly different wavelength regime, and something that I'm very excited for Lupita to work on as part of her thesis work is trying to constrain the temperature of these flares using these two different missions with slightly different wavelength coverages. So we're going to try to use statistics and a little bit of luck to see if we can constrain the temperature of these events, which is really interesting from talking about the energetics of these flares. One thing that we started working on back in my dissertation, and hopefully we will continue soon, is understanding these complex events. So this explosive event that I've shown you that Lupita's model reproduces is very simple. It has an exponential rise, or explosive rise, and a double exponential decay. But many flares do not have this profile. Many have this much more complicated structure. This is just one example where we have very naively let a machine try to just pick out all the peaks and decompose this and try to understand what the physics of the event, what the structure of the event might be on the surface of the star. When we see a big flare, a super flare, or something like the Carrington event, which happened a couple hundred years ago, which we worry about from maybe an astrobiology standpoint, they don't have simple light curves that rise and then smoothly decay. They have multiple peaks. There are multiple explosive events. They can possibly trigger other events near them. They're very complicated. And so understanding the statistics and the composition of these events, I think, is a real interesting challenge. Okay, here's other weird ones that look weird. There's lots of good model fitting tools here that needs to be developed. One of my favorite aspects of the Kepler flare work has been statistics, the very dry field of statistics that we often do when we're in astronomy, where we collect butterflies and count how many butterflies we collected. Like most things in the universe, there are lots of little things and very few big things. And so too with flares. We see, this is my cartoon illustration of this power law relationship between the occurrence rate of the flares and the energy. So there are very few high energy flares, ones on the bottom right here that you would be worried about. They thankfully don't happen very often. And there are a lot of little flares. And in case of GJ1243, we saw again a little flare every hour or so. This power law relationship we see on other stars is also seen on the sun over something like 10 orders of magnitude. So this is how the sun acts, and this is how other stars act as well. And one of the great things about the Kepler mission was being able to do these statistics for lots of stars. And so this is one example of stars all of a similar temperature, where we gathered flare statistics and then put them on this flare frequency distribution, this occurrence rate distribution. And the fast ones, the young stars, all have higher distributions. And the low ones, the slower rotating stars lose angular momentum over time. These slower stars have lower flare rates. And one student told me this looked like a rainbow or maybe a unicorn. And so we call this the unicorn plot now, which I think is great. This has given us some kind of model to predict how many flares a star will produce as a function of time. And we tried to do this as a function of mass. And so this is a busy, obnoxious plot where you're supposed to just understand that we've cut this into different bins of mass. There are big stars and little stars, and we have lots of bins. There's a bunch of awful selection effects here, which make this actually really hard to use. So we can find trends, but we're having a hard time making useful predictions for people like Rory. And I owe you an email. But still, this is the first time we've been actually been able to do this work and to see this nice rainbow effect of the flare frequency spreading out as a function of time and mass. So we're learning a lot about stars, which is hopefully a use to people who care about things that might go around stars. And so at the end of the Kepler mission, which occurred not too far off from the end of my dissertation, which was not my fault, at the end of the Kepler mission, we had this picture that we sort of had before, but we actually had details. We understood that the sun, thankfully, is a fairly inactive star. This is a different measurement of magnetic activity spectroscopically. This is a plot from before the Kepler mission, which we understood young things had more flares and more magnetic activity on their surface, and older things like the sun had fewer flares, less activity. And so this is good. This model, this understanding of age and activity and how things like rotation fold into it was all well in hand. We thought we understood all of this, which is great. And so at the end of the Kepler mission, we were fairly satisfied. The K2 mission, its extension, we did a little bit more flare work on. We were fairly satisfied that we understood these short time scale variations that we call flares and star spots. We had a good model of these things. There's lots of details to still work out, but I sort of stepped back from that work and started thinking about other things. And so for the last few minutes, what I want to talk about is where I think this work is going and what I'm interested in doing over the next few years. And which is going back to this exact same thesis, which is the sun is not constant in time. And so here, instead of showing you a video over a couple hours where you see a flare go off, here I'm showing you the sun. On the left half is the sun at solar maximum. And then on the right half is about 5.5 years later at solar minimum. And the sun goes through these periods of active maximum and active minimum every 5 or 6 years. It's an 11-year cycle. And it's been going on, well, we've been measuring it since the time of Galileo. And this, we call it the so-called activity cycle, presents a different sun to us year to year, right? The sun goes through these phases of high activity with lots of flares and then almost no activity, very quiet, very calm. And then there are longer term decade and century and maybe millennium timescales that we don't understand. But I won't live long enough to see them, and so it's fine. And so this discontinuity in time is also really fascinating, that this activity cycle presents a different star on any given year. Another way to look at this, the most famous way of looking at this, is the so-called butterfly diagram. This is a nice version of it that Brett Morris, again, a former AB student, made in a recent paper, showing for the sun, the emergence, the latitude on the sun, and the number density of sunspots over time. And what you can see is this during active maximum. Wait, does this laser pointer work? During, maybe? No, okay. During stellar activity maximum here, these periods of maximum activity, there are lots of spots and they tend to occur at low latitudes. And the sun goes into this kind of quiet phase and the cycle begins again. And then there's lots of physical reasons from the solar standpoint, why there's a trend in time with latitude, and there's a magnetic field reversal, and there's lots of cool solar physics here. But again, year to year, you can see this cycle beginning over and over, the sun going through quiet and loud phases over and over and over. The most famous way of tracking that is sunspots. There's been a lot of work trying to track this with star spots for other stars as well. But what's interested me is that there are many other tracers of this activity cycle as well, primarily flares. And so here are two other examples on the bottom. So on the left, you see sunspot area over time. You can see the cycle very nicely. And then on the bottom is the flare index. It's like the number of flares per day that the sun's producing. You can see the exact same cycle being traced out in flares as it is in sunspots. So you can see a factor of at least 10 variation in the number of flares per day that the sun is producing, which is cool. And on the right is kind of a hard to look at plot, but you get the same idea that it's a logarithmic scaling, so it looks kind of like it flattens out. But you can see flares of different energies, all the high energy flares and the low energy flares, they all have the same behavior. They come and go on this 11-year cycle. And just to view this in one more way, which is again that sort of cumulative distribution, that power law distribution. Here is that power law of this peak flux, which is equivalent to, or analogous to energy, and then the occurrence rate on the y-axis. And you can see active maximum in red and active minimum in black. These are X-ray flares. The point being here, there's a factor of 10 at least variation in the cumulative number of flares per day the sun produces from active max to active min. And so if you were to go to a star at any given day and count the number of flares, it would depend on where in this cycle you were, if you tried to understand how active that star was. The takeaway I had from this is that flares are a really good tracer of activity, that they are a really effective tracer of activity on our sun, and so too they should be on other stars. And this has been so far almost totally unexplored, flares as a tracer of long-term behavior. For reasons that I can go into, flares may actually be better than spots for other stars. They're really good for the sun because we can see the surface of the sun, we can count the number of spots. On other stars, we're trying to infer the number of spots from like the integrated light, and there's lots of degeneracies in trying to integrate that. So Rodrigo Luger, who is another former AB student, has done really heroic work with statistics trying to actually back out this variation and see if you can measure these cycles, and he thinks you can, but you need enormous samples of data to do it. And we don't have that for most single stars. And so I think in the absence of like nearly unlimited data, I think flares may actually be better because we can count the individual events. We can go through and just count the number of events per day. And counting is simple, and I like simple things. And so Kepler launched in 2009, unfortunately it has died. TESS launched in 2018. It is currently 2022, if you're watching this from the future. And so we have more than a 10-year baseline now of space-based photometry, precision light curves like this, like shown here on the bottom, where we can go and in great detail measure the number of flares that a given star is producing as a function of time. We have a long baseline now and precise data. So we have the capability now to do this. And so we go back to our favorite star, the one that entranced me back in 2009, 2010, 1243, go back to this cartoon of flare occurrence rates. And I will just put down the Kepler and the TESS data, and they look exactly the same. Let's see, yeah, here we go, boring. So these look exactly the same. This is the same distribution. The star has not changed at all over 10 years. Now, Kepler had more precision, and so we're able to get down to lower energies, and the error bars are smaller, and there's lots of complicated bow ties. Let me see if I can back up here. There we go. Yeah, so the bow tie in this direction is the signal of noise, and the bow tie in the vertical direction is the sample size. So they're a little bit hard to fit things to because of the two-dimensional errors. But the point is these two lines go through each other. This is an incredibly boring plot. And that's why it's interesting, right? Because it's very boring. Because here we came back a decade later and nothing had changed. The star looks exactly the same. And when you try parsing the data up month by month, this month versus that month, the star just is constant. Nothing is changing on this star. Thank you. All right, so boring is interesting, right? Because it's very different than what we expect from the sun. And here is an example from another star, only a little bit more massive than 1243. And here's an example from month by month of TESS data that we've been watching. So we knew it was a flare star from Kepler, and now TESS came back and re-observed it years later. And month by month, you can see in the middle, there's a month where the big flares disappeared. The thing has ceased to have big flares in August 2019. We came back a couple years later, July 22, August 22, the big flares have returned. And here's another measure of flare behavior. This is like the total integrated flare output. This is the flare activity fraction or something. And you can see the Kepler data on the left, and there's variation month to month, but it's all kind of constant. And then we came back with TESS, and the star has become less active, and it seems to be like there's long-term trends. So this is hot off the press. We haven't published this yet. This is a plot I made 2 weeks ago. But this is the hint that maybe there is some long timescale activity cycle at work, changing the number of flares per day the star is producing. There's a lot to do here. There's a lot to understand in the month-to-month variation, which has been totally, the short timescale variation is unexplored. Again, GA 1243 was almost identical month to month, no change. Whereas here, this one changes by up to an order of magnitude month to month. There are some of these months, this like blue dot hanging down here in the middle, this blue dot is real. Like there really is, like the star just kind of forgot to flare for a little while, and then it came back the next month. So there is actually very large variation month to month that you might see. And then you can see over a decade timescale, this is 5,000 day baseline, you can see there is a factor of at least 10 variation in the total flare output. And again, month to month variation as well. So there's a lot to do here just on understanding the statistics of what we're seeing when we take a snapshot, a point in time measurement of the flare rate that a star is giving us. And so I'm really excited that we've had TESS cycle 3 and cycle 5 funding to do this work. Cycle 3 is the first 2 pink dots, cycle 5 is the second 2 pink dots. We got the one in the middle for free. And then just last week, we were actually really excited to have NASA ADAP award come through. And so that will provide funding for about 3 years for this project to do statistics on Kepler and TESS and also ground-based follow-up for this, which is really exciting. And so there's lots to do, right? There's lots of stars to observe. Kepler observed something like 200,000. TESS has observed a few million stars. Something like 100,000 of them have long-term monitoring year after year. And so there's lots of stars to go after and to do this point-in-time flare estimates. And so here on the left, this is the star I just showed you, Kepler and TESS, long-time monitoring. On the right, this is a new candidate we have. We have only TESS data. This was not observed by Kepler. But you can see just from a couple seasons of TESS, month to month, again, lots of variation in the flare behavior and possibly hints of long-term evolution just from TESS alone. And TESS continues to observe, thankfully, may it last forever. And so we will continue to get data for this star in particular every other year for the indefinite future, which is exciting. And there's fun challenges in terms of how you combine data with different error bars and fitting them properly, which I'm just illustrating in the middle, that some fun numerical challenges. And so if any of this appeals to you, please do reach out. And so I'll end just by one more time saying that like the sun and other stars are not constant in time. And this is an opportunity in this time domain statistics era to like understand these variations. And so if the sun or other stars and magnetic activity in particular appeals to you, or things like binary stars, rare stars from big surveys, or SETI, which is an area that I've been working on a lot over the last couple of years. If any of these areas appeal to you, then I'm in B315, I think that's my office number, and you can come up to me on the 3rd floor and let's chat and have coffee. And that's what I've got.
Thank you very much, Jim. We have time for questions. Don't feel free calling people.
Yeah, and pull the chat too, so. Yeah, Rudy. Yes.
Rudy.
Sorry.
Yeah.
Do you mind if I ask like 2 questions?
2 questions, sure.
First is, what extent is the this butterfly cycle on the sun like an empirical kind of thing, and to what extent has that been motivated by, or maybe enforced by like stellar interior models?
Okay,
what's
so
going on inside?
So the question is, to what extent is the 11-year cycle that we see just an empirical cycle, or is it actually supported by models? Okay, so it was discovered hundreds of years ago, and so it's very empirical at that time, right? Like we see this, and it's very curious. People just, again, making pictures of the sun by hand and measuring the number of star spots or sunspots over time. It has become, this activity cycle, this 11-year time scale has become a really critical benchmark that you have to hit in dynamo modeling and understanding like how the interior creates magnetic fields and how it stores it and why the polarity shifts, right? Because the North and South Pole flip every 11 years, so a full cycle is actually 22 years. And so making sure that that's like a key number you get, that if, when the sun spins at 25 days and shows a certain level of differential rotation, and you get that time scale out, is a key measurement that you have to hit with modeling. And so the Babcock and Lighton model from like the 60s was very successful, the so-called mean field model was successful at sort of generalizing this and painting a picture of kind of how the sun operates, sort of a toy model. And then if you want to know a lot more about how this works, you ask somebody like Sean, who's sitting in the back, who actually makes these kinds of numerical models for a living. And Maysby knows the real answer.
And I had a quick follow-up, if that's okay.
Yeah.
So how much do those models change for modeling like M-dwarf stars or things like that? And can they kind of explain why one particular star might have no activity cycles or a very different periodicity on their activity cycles?
So the question is, how much of these models change star to star? I would say they change wildly model to model and group to group. There are general predictions about rapidly rotating stars having weaker cycles, and then at some point the dynamo and convection calm down enough, and the magnetic field strength quiets down where you can actually have enough shear. And now I'm reaching, and I don't understand the models well enough to know the answer. But like at some point they do become more prominent. And there were historical observations 50 years ago where we thought we understood rotation and cycles, but this all seems to be muddled the more we get more data. And the problem is, to measure these things, you need decades of data, right? And like this becomes the real challenge. So the Mount Wilson survey, spectroscopic survey, has data from the 50s and the 60s that it draws on and continues today, but for hundreds of stars. And what we see there is some stars have really well-behaved cycles, like the sun. Some stars have chaotic variations, and some stars have no variation at all. But we see kind of all possible variations, all kind of possible behavior. And I would argue we don't have the statistics to really understand why. And that's why NASA's going to give me a bunch of money. Yeah.
That was a very interesting talk, and I'm not being from this field, I'm very surprised that we even made that kind of measurements before, like the amount of flares and the variability of like for a very large number of stars. And so I guess like where you're gonna get with all these new data are like hopefully like some variation of the cycles for different stars.
Yeah.
And also the amplitude of change. And so, as you said, we don't have enough data yet, but what is your gut feeling? Like, what, for example, like M-dwarf, are you going to expect to have like a larger amplitude in shorter cycles, or the other way around, and what you expect for, for all the types of stars that are like, just if you have like an idea?
My gut feeling is we're going to get a lot of stars. Sorry, the question was surprised that we don't have these kinds of measurements before, which I'm always surprised with as well. But also it's really hard. It's hard to do this from the ground because the sun comes up and it makes counting things difficult when they're stochastic. So it is actually really difficult. 1 month of test data is like a revolution compared to 20 years ago. And so the question is, do I have any gut feeling about what we're going to find as a function of mass? Like, will the M-dwarf show more cycles? My sense is that the really young stars that produce the most flares will have the highest flare rate and probably the least amount of variation long term. I think they'll show chaotic variation on short time scales, but will be, yeah, just pull me if you want. What will show though, like, I think I just killed the owl though. Oh. It's okay, you'll be able to get it back. But we'll show like the least amount of coherent long-term variation. And so one of the open questions, one of the good boundary conditions is like, at what point do the activity cycles actually show up? When do you start seeing this kind of long-term behavior? Even if we can't constrain the cycles, when do you start seeing actual long-term trends, which would be suggestive of an activity cycle? I think that's a really interesting like boundary condition that we're going to be able to probe. Yeah.
Okay, another question over there?
Hi. So I guess my question is about the observation that is not following. There's kind of like the outliers on, for example, the spectrum, like the parallel spectrum that you observe. Have you seen any noticeable examples? Because since you mentioned about SETI in the last slide, I think I remember some news article talking about the idea of Dyson spheres showing up in observation. I want to ask a bit more about this kind of weird behavior that we can really get from that case.
So the question is, I'm not sure if the Zoom can still hear me. The question is about power laws and the distribution of events and then the connection to SETI.
Yeah, like the anomalies, like the things that need to explain, like
So I'll say I haven't seen any variations in flare activity that make me think of aliens, which I should say right off the bat. I don't have any good candidates for alien activity. we do, okay, it's good. We do still see power law distributions over many spectral types and many ages. There are hints that some stars break that power law distribution, both at possibly the high energy end, because flares cannot continue to infinitely high energies. At some point, the star would explode. And there is hints that it might deviate at the low energy end, though it's very difficult. And on the sun, it seems like it continues into what we call nanoflares, so it's unclear. So there are hints of trying to fit broken power laws that may be interesting. And then I'm going to punt on the SETI question because I think it's too open-ended, but I think it's really interesting in the statistical astronomy era that we ask it.
Another little arrow. Yeah. No,
Getting some good feedback.
well, we're working on some technical difficulties here, so if there's more questions, go for it while we sort this out.
Yeah.